Let's consider a simple nonlinear device as a mixer, but the nonlinear device in particular is the PN diode, is a PN junction diode over here. Why it's nonlinear? Because you recall that the IV characteristics of a diode is not linear. It's an exponential behavior of the current with applied voltage, or it's something like this. So IV characteristic of a diode is nonlinear, it's exponential. So diode is the nonlinear device over here. So we are not considering the diode as a switch or a rectifier, but we are exploiting this nonlinear relationship of the diode for mixing of the RF and local oscillator energies or signals. So the figure shows a single hypothetical, it's a hypothetical single diode mixer circuit. So what the first op-amp does is over here, so let's call this as V1. This V1 is equal to VRF VLO because it's a summing op-amp. You see, since op-amp has an infinite input impedance, and this point is also a virtual ground, since op-amp is not drawing any current inside of its non-inverting or inverting inputs. So all the current is being passed through the feedback resistor R. So what we have is, you see, you can write this V1, you can express V1 in terms of the input VRF and VLO as minus R over R. So because since the input is at the inverting and the non-inverting input is grounded, so we have minus R over R VRF. This is minus R over R VRF. Then the other signal is, we have this from the local oscillator as well. So it's again the ratio of minus R by R, minus R over R VLO. So you can see that you have this the output as minus of VRF plus VLO. So this summing voltage is applied at the input of the PN diode, which is a nonlinear device. And for small signal conditions, I mean the VRF and VLO is small. So let's consider small signals. VRF. We assume that VRF and VLO are small, or let's say they are much less than the V thermal voltage, or 26 millivolts. They're much less than 26 millivolts. Where does 26 millivolts come from? I'll explain that in a moment. So we assume that VRF and VLO are small, and we exploit the nonlinear IV relationship, that is, expand the exponential into series and see that how this mixing occurs. And for the second op-amp, from where we take the output, you see V out is nothing but, since there is no current that can go inside the op-amp in either of the op-amps. So V out is nothing but it's I, which is the nonlinear current of diode, multiplied by R. So the second op-amp is a transconductance amplifier. It's a current to voltage converter. So input is the current, input is the diode current I, okay, and this current then flows through this R, then goes inside the op-amp, and the output is IR, which is the voltage, which is the nonlinear voltage that we have. And this I shall consist of the nonlinear or mixing of RF and LO signals to see how it is. So you see the input of the second op-amp is at virtual ground. So therefore this is also grounded. So the full sum voltage is being applied across the diode. So this V1 is being applied over here, and then we have this nonlinear I. So with the feedback resistor, the second op-amp is current to the voltage converter, as I've explained. So it produces a voltage proportional to the current. So it's a current to voltage converter. Now, the relationship of this current to voltage, applied voltage, is V is RF. This applied voltage is your RF and the local oscillator voltage signals, and this VTH is V thermal, which depends on the temperature on the absolute temperature. K is the Boltzmann constant, Q is the electron charge, so this is fixed, and it's a small voltage. So previously we have assumed that our RF and local oscillators are small voltages, and therefore we are considering small signal conditions. We are not considering diode as a rectifier for large signals, or we're neither considering it as a switch, but we are exploiting the IV relationship of the nonlinear device we are exploiting the exponential characteristics for the diode, and see how this nonlinear characteristics can for small signal conditions can produce the mixing outputs. So over here, for small signal conditions, we assume that the applied voltage V, that is VRF, VLO, is a small voltage, and then this exponential current I can be expanded in series. So if you expand the argument of the exponentials, so you have your V thermal, then V over V thermal square 2 factorial cube, and so on. So you don't need to go on, because V is small, so the next higher terms are small. You don't need to go on, continue any further. So you see that this is your saturation current multiplied by R, and this is what you get at the output. This is current to voltage converter. That's what you have at the second op-amp. Now you see the first thing to notice is so this is the IS exponential V, and we have expanded this in series, and this current multiplied by R is what you have at the output. Multiplied by R is, and then we are expanding this over here. Now the first term suggests that this is an unbalanced mixer. Why it's an unbalanced mixer? Because you have this V as VRF, VLO, and this energy from the ports RF and the local oscillator ports, it comes directly, it feeds through the output. So this is an unbalanced mixer, you see. Then you have the second term is the square of V thermal squared, and this term shall produce a cross product terms like VRF into VLO. So you have VRF, VLO, and then you will have squares of the terms. So you will have, for example, you will have VLO square, then you will have VRF square. Now the first term in this expansion gives you the sidebands, the double sidebands, the sidebands around the local oscillator frequency. Okay, and similarly for the third term, you will have the RF band shifted across the third harmonic, and so on and so forth. The things continue. Then I mean you can filter out these undesired double sidebands which are far away from the local oscillator. Okay, frequency. Now so you see the first term that is giving you a feed through, there is no balance, so both RF and LO frequencies appear at the output. The second term that dictates that is being dictated by a square law term will produce the desired upshifted and downshifted sidebands, since the square will contain the cross products. So you will have this sideband from this term. This term also produces the bias term and double frequency components. So you will have this double frequency components over here, and you will have the sidebands from the first term. The third term will give the output at the third harmonics of the RF and local oscillator frequencies, and also you will have those terms 2RF omega LO, 2RF minus omega LO, similarly 2LO plus RF, 2 omega LO minus RF. You know that the mixer always creates new frequencies. That's why it's a nonlinear operation. Multiplication is inherently a nonlinear operation. In RF mixing, it produces new frequencies. So normally these products are far removed from the desired output band. For example, your desired output band is around the fundamental omega L. You can band pass filter it out, and you can leave the rest out. So they can be filtered out. So now, so this is an AD schematic. Let's try to understand what is happening. You see over here, you have the same resistances. Okay, so this is 10 ohms, this is 10 ohms. The feedback resistance is the same as 10 ohms. So what I expect at V sum, once I simulate the dual tone harmonic balance, is that this V sum, first of all, will have two frequencies. One is the local frequency and local oscillator frequency, and the other is the radio frequency. And what I've said for the LO, local oscillator, and the RF is 110 respectively. So let's have a look at the first the V sum and the VRF LO. So you see this is the plot of the RF and LO, both time domain signals. You see this blue one is RF, which is 10 Hertz, so this is 100 milliseconds one cycle. So you can see the frequency of the blue one. The blue one is 10 Hertz, and the other is the local oscillator. It's 100. So there are up until this point over here, there are 10 cycles of LO for the local oscillator. There are 10 cycles. Okay, and you can see at the magnitude spectrum as well, the same thing. This red magnitude spectrum is for the local oscillator. So it is, as expected, this is 100 Hertz. Okay, this is 100 Hertz. And then you have 10 Hertz for the RF. This is 10 Hertz. And that the blue, this corresponds to the blue time domain signal on the top. And this is your RF signal. Now, both signals are first combined to yield V sum over here. And you can see that this signal is 1, it's not 2. So over here we actually, it's the same graph depicting two different signals, so you have two different colors. So but this is the same. After summing this V sum is VLO plus VRF. So let's see, this is V sum is VLO plus VRF. Okay, and what we have at the output, as expected, is we have this 10 Hertz signal and we have this 100 Hertz. So both are combined over here. Now, what happens next is, so this is a symbolically defined block. What it's doing is, I've defined a nonlinear current relationship with the voltage. So this is the expansion of the exponential over here. And this V1 is the port voltage. So whatever is the port voltage over here is defined as such, and then the output is the current, which is being measured by the probe. Okay, and this current flows through the feedback resistor of 10 ohm to produce V out as your I diode. This is your diode current, the nonlinear diode current, multiplied by R. Okay, so whatever is the diode current it has to be multiplied by 10 ohm, which is 10 times that the diode current. That's the output voltage. So let's have a look. You see, this is my diode current, and 10 times of this is my output voltage V. This is voltage, and that's the current. Okay, at the input of the second op amp, the output is voltage, so it's a current to voltage converter. And in the frequency domain, you see that you have the frequency component DC. That is expected. You have this is DC term. Okay, you have this DC. This corresponds to the RF signal. This is an unbalanced. I told you this is an unbalanced mixer. So you have this RF exactly at 10 Hertz. The next component is the lower sideband, which occurs at the fundamental frequency of the carrier of the local oscillator signal. That is 100 Hertz. So you have the carrier, first carrier, then you have the harmonics. Okay, so these are the carriers. These are the carriers and harmonics of the carrier, and then you have the sideband as expected, because there are cross multiplication of the terms over here. You see cross multiplication of terms like this. For example, this is the third, and for the third term there is a shift at third harmonic, and then there is also a 2 mega RF, omega LO, 2 mega RF minus omega LO. So there are new frequencies which is being created and dictated by these terms. So this is what we are looking at over here. So we have this is not a suppressed carrier. This comes out with a carrier, so it's an unbalanced mixer.